Hello friends, today's question: a wedge of mass m and triangular cross section with AB is equal to BC is equal to CA, which is equal to 2R, is moving with a constant velocity minus V iota towards the sphere of radius R fixed on a smooth horizontal table as shown in figure. The wedge makes an elastic collision with the fixed sphere and returns along the same path without any rotation. Neglect all friction and suppose that the wedge remains in contact with the sphere for a very short time delta t, during which sphere exerts a constant force F on the wedge. Find the force F, the normal force N exerted by the table on the wedge during the time delta t. And part B, let H denotes the perpendicular distance between the center of mass of the wedge and line of action F. Find the magnitude of torque due to normal force N about the center of the wedge during the interval delta t. So we have this table and a sphere of radius r, and this sphere is fixed, whereas this triangle, which is in equilateral, is moving towards this fixed sphere with the velocity v, and then it makes an elastic collision with the sphere and returns back with the same velocity, and the contact between them is only for the time period delta t. So let us redraw the figure of their collision. So we have a sphere of radius r, and this is the triangle, and they make a contact for a very short time delta t, and we have force, let us suppose that is F, and you can say that this is the equilateral triangle, so this angle will be our 60 degree, and we can draw two components of the force. So this angle will be about 30, so we are going to have this as F cos of 30, and this will be F sin of 30. Okay, let me redraw it here once again. So we have a force F, and this is a point of contact, and it can be divided into two components. This will be angle 30. This is force F. So we are going to have x component as F cos of 30, and we are going to have y component as F sin of 30. And this is our triangle. This angle is 60 degree. So therefore, we can say that the force acting on the wedge can be divided into two components. You can say the force F acting on the wedge is going to have two components along x-axis, will be f of x, and this will be equal to f cos of 30, and we are going to have along y-axis, let us suppose f of y, and this will be f sin of 30, and it is given that the collision between the two is elastic. You can say the collision between the sphere and wedge is elastic, or rather we can say fixed sphere is elastic. Therefore wedge will retrace back with the same velocity, Therefore we can say that the motion of the wedge is entirely along x-axis. Motion of the wedge is entirely x-axis. So we can say the force that is responsible for the motion of the wedge is in x direction, or we can say that is f of x. Therefore we can say that impulse, as they meet each other for the fraction of second, that is delta t, so we can say impulse will be equal to change in momentum. And impulse is written as force, which is f of x multiplied by delta of t, and we have change in momentum, that is mv minus of minus mv. This comes as twice mv, or we can say f of x is equal to twice mv divided by delta of t. But we already know f of x is f cos of 30. We substitute it here, we can say f cos of 30 is equal to 2 mv delta of t. We substitute value of cos 30, or we can say f is equal to 4 mv square root of 3 delta t. Now we can say from the figure itself that force F is in along x-axis and as well as y-axis. Okay, we already drawn it like this. This is our fx and this is our fy, and the coordinate is like this: x-axis, and it is given y-axis and z-axis. Okay, so this is z-axis and we have this as y-axis. So we can say our f is equal to vector form fx unit vector I plus fy minus unit vector k. We substitute the value. Fx we already know is our f cos of 30 unit vector I plus fy is f sine of 30 and unit vector minus of k. So we can substitute the values. We get f square root of 3 by 2 unit vector I plus f 1 by 2 and minus k unit vector. From here we can take f by 2 as common. So f by 2, we get this as 3 unit vector and minus k unit vector. Substituting value of f, which we already know, let us call this equation number 1, and this is equation number 2. You can say using equation 1 in equation 2, you can say our f is equal to, this will be equal to f is 4mv square root of 3 multiplied by t by 2, and this is 3 unit vector minus k unit vector, and we get 2 and 2 cancels out. So from here we can say f is equal to 2mv root of 3 delta t, and this is delta 3I minus k unit vector. Let us call this as equation number 3. Now we are supposed to find out the force F, which we already found out. So this is the value of the force. So we can say this is the value of force F. And next we are supposed to find out the normal force exerted by the table on the wedge during time delta t. So let us draw the wedge. So this is our wedge. Mass is given as m, so we have mg in the downward direction, and here we have f sine of 30, and we are going to have a normal because of the table. Let us call this n. Therefore equilibrium in z direction, you can see equilibrium in z direction, because it is said that it makes an elastic collision and returns along the same path without any rotation. Okay. So it means the wedge will be equilibrium in vertical in z direction also, as there is no rotation. So we can write the equation as n is equal to f sine of 30 plus mg. So we already know value of f. So we can say we get normal n is equal to 2mv square root of 3 delta t plus mg. We can write it in vector form also. You can say n vector is equal to mg plus 2mv square root of 3 delta t and k vector. Okay. This is in the vector form. In vector form. So herein there is no, you can say, rotation also this in the wedge. Okay. So because of this, the rotational equilibrium will be also in balanced form. Here we can write as there is no rotation in the wedge, therefore will also have rotational equilibrium. Rotational equilibrium. Now this equilibrium of the rotation we are going to use in the B part, where it is given that line of action of force and the center of mass has a distance h between them. So this is our wedge, this is our center of mass, let us suppose C, and we have a line of action force in this direction, and the distance between two, it is given as h, and this is our normal force. Therefore, as there is rotational equilibrium, okay, so we can write that anti-clockwise torque because of F will be equal to clockwise torque because of normal N. Therefore, we get anti-clockwise torque because of F anti-clockwise torque of F is equal to clockwise torque due to N. Or we can say the magnitude of torque of normal, that is N, about center of mass will be equal to magnitude of torque of F along center of mass. Which will be equal to the force F and the perpendicular distance h. So if we denote the torque as tau n because of normal, so we already know value of force, so we can say torque normal, the value of magnitude F is given as 4 mv square root of 3 delta t multiplied by h. Okay. So this is the, you can say, magnitude of torque due to normal force N. This is the magnitude of torque due to normal force N about center of mass. So in this question there were two important things. First of all, that it is given that the entire motion is only along the x-axis. So therefore we are going to consider it only the force which is acting along x-axis. And secondly, it is also given that without any rotation. It means all the forces, or we can say torque, acting on the wedge will be also in the balanced form. So it means anti-clockwise and clockwise torque will be equal to each other. So these are the two properties which are used in order to solve the question. So this completes the question. Thank you.